In the previous slides, we have talked about mutex lock, which is used for process synchronization. In this slide, we are going to talk about the other more sophisticated one, which is called Semaphore. It can provide more flexibility than mutex locks to synchronize the process activities. So generally, we use S to denote semaphore. Later, you will know that the semaphore is essentially an integer variable. And this integer variable only accessed through two indivisibles, or as we have mentioned, two atomic operations, wait function and the signal function. So they are originally called P function and the V function because one inventor of the semaphore is de Castro, who is from Dutch. So P function and the V function are first letter of two Dutch words. So P function means try, V function means increment. So that is why in the original operating system research, they are called P operation and V operation. You may want to remember these two terms because later you may get an interview from Google or from, for example, Facebook. So they may ask you that, tell me the process synchronization mechanism with a P function and a V function. So actually, they are talking about the semaphore. And actually nowadays, P function and the V function are still widely used in operating system in terms of a semaphore. However, in this course, we will use another two terms, wait operation and the signal operation for the operations because they are more easier to understand. So basically, wait operation is equivalent to P function, and the signal operation is equivalent to V function. Then let's see the definition of a wait operation first. So one thing need to be careful. When you execute wait operation, it cannot be interrupted because it is indivisible or atomic operation. The wait operation will take semaphore as a parameter. Inside the wait operation, we have a while loop. It will check whether the semaphore S is less than or equal to 0 or not. If yes, the process will be stuck at this while loop. Otherwise, the process will be out of the while loop and decrease the semaphore S by 1. On the other hand, the signal operation also needs to be indivisible or atomic. And the definition of a signal operation is quite simple. It just increases the semaphore S by 1. Then let's see how can we use the semaphore for process synchronization. Basically, there are two types of a semaphore. The first type is called counting semaphore. So for this type, the integer number associated with the semaphore can be in unrestricted range. So which means you can set the value from 0 to any number as large as you want. Another type is the binary semaphore. So basically, the functionality of a binary semaphore is very similar to mutex lock, and it can be simply implemented by a counting semaphore. It is quite simple. So you just set the integer to be 0 or 1. So when you want to get the lock, you just set the semaphore as 0. If you want to release the semaphore, so you just increase the semaphore to 1. So binary semaphore and the mutex lock are essentially the same. As we have mentioned that semaphore is more flexible than mutex locks, so it can solve various synchronization problems. At the bottom of this slide shows you example how to use a semaphore to solve a synchronization problem. So we have two processes, P1 and P2. So we require instruction S1 to happen before S2, which means that we have to execute S1 first, then execute S2 second. So even though they are in different processes. And we also create a semaphore called SYNCH and initialize it to 0. So here we suppose P1 has been put onto the CPU first. Then S1 executed and called signal operation. Since currently the value of SYNCH is 0, so after we call the signal operation, the value of SYNCH is increased to 1. After a while, P1 has been interrupted by P2. Then put P2 onto the CPU. Then P2 will call wait operation. Since SYNCH is 1, which is higher than 0, so P2 will be out of the while loop and decrease the SYNCH by 1. So SYNCH becomes 0. Then execute S2. So in this case, S1 is executed before S2. Then let's consider another situation. So we put P2 onto the CPU first. Then P2 calls the wait function first. Since SYNCH is 0, so the condition of a while loop has been satisfied. So P2 will be stuck at the while loop until P2 is interrupted by P1. Then P1 is put onto the CPU. Then execute S1 and calls signal operation. Then increase the SYNCH to 1. Later, P1 is interrupted by P2. So previously, P2 has been stuck at the while loop because SYNCH is 0. However, since SYNCH has been increased to 1 by P1, therefore P2 will be out of the while loop and decrease SYNCH to 0. Then execute S2. From the aforementioned situation, we can see that so no matter we put which process onto the CPU first, so we can satisfy the requirement that S1 is executed before S2.